Hey everyone, and welcome to today's Explainer. Let's jump right in, shall we? Today, we're unpacking a truly fascinating piece of computer architecture. Specifically, we're looking at Chapter 24, Appendix C, all about interleaved memory. If you're the kind of person who loves understanding the hidden physical layouts and the clever math that keeps our processors from just sitting around waiting for data, well, this is the Explainer for you. We're going to get right under the hood.
I want you to think about this for a second. How exactly does your computer manage to load a massive, multi-gigabyte app or stream a 4K video instantly without stuttering? We almost always give all the credit to the CPU, but here's the thing. A processor is really only as good as the data fed into it, right? If your memory can't deliver that data fast enough, the processor literally just stalls out. So the real secret to that lightning-fast performance isn't just raw processing power. It's actually the highly optimized highway system moving data from your computer's memory to the processor.
To really understand this highway, we first have to look at the starting point. Main memory is typically made up of a series of DRAM chips, and a specific grouping of these chips forms what we call a memory bank. Now, this bank has a port used for transferring data to and from the processor or an intermediate cache. You can think of a single memory bank kind of like a single dedicated checkout lane at a grocery store. It works perfectly fine, but all the customers, or in our case the data, have to pass through that one lane, one right after the other.
And that brings us to our first major hurdle, the memory bottleneck. A processor needs an absolute flood of data, and moving it efficiently is our fundamental challenge.
So, the system tries to solve this bottleneck from the controller side using something called a burst access. See, the memory controller doesn't just ask for data one tiny piece at a time. That would take forever. Instead, it performs a single bus transaction that reads or writes multiple words all at once. For example, a cache might have a line size of 4 32-bit words, so the data gets transferred in blocks of 4. Going back to our grocery store analogy, it's like trying to process an entire shopping cart of groceries in one single motion, instead of scanning every individual item. But even with the burst access, the physical layout of those memory banks still dictates how fast that cart can actually get processed.
To truly appreciate how we fix this, let's look at the baseline. Welcome to non-interleaved memory, or as I like to call it, the slow lane.
If a memory controller doesn't support interleaving, memory addresses are assigned sequentially in the first bank, and only when that bank is totally full do they move on to the second one. Because all the words in a block are coming from one single bank of DRAM, the time it takes to complete the transfer is just linear. It's strictly sequential, like trying to shove all your data through that one painfully slow checkout lane. Now, sure, contemporary DRAMs do have a feature called page mode access, which is basically a form of on-chip caching that makes the second, third, and fourth words load a bit faster than the first, but at the end of the day, it is still a linear process. Interleaved memory, on the other hand, alternates those addresses across multiple banks. So let's look at the elegant engineering solution that gets us out of this traffic jam. Enter interleaved memory, the express lane.
You can really see the difference when you look at these timing diagrams. Up on top, you've got the non-interleaved timing. Notice how the first, second, third, and fourth words just strictly follow one another, clock cycle after clock cycle. It's a straight, linear sequence. But now, look at the bottom diagram. This is interleaved memory timing. The addresses alternate between bank 0 and bank 1. Because the 4 words of that burst access are actually spread out across 2 physical banks, the individual accesses can overlap. So while bank 0 is busy dealing with the first and second words, bank 1 is simultaneously handling the third and fourth. This overlap hides part or sometimes even all of the natural DRAM access time delay. It's literally doing 2 things at once.
And the math behind this efficiency is actually pretty simple, represented by the variable k. You can connect multiple memory banks to form an interleaved system. And because each bank services a request independently, an interleaved memory system with k banks can service k requests simultaneously. It's that straightforward. This increases your peak data transfer rate by a factor of k. So if you have 4 banks, your peak transfer rate goes up by a factor of 4. And just as a quick side note, in most systems, that number of banks is usually designed as a power of 2.
Now, you might be wondering, how does the computer manage all this parallel data without causing total chaos? Well, it comes down to directing traffic with memory addresses.
Take a look at this routing structure right here. We have multiple memory banks, all connected to a single data bus, or channel, from bank 0 all the way down to bank 2 to the power of k, minus 1. They share this bus by utilizing time division and overlapping operations. But the real magic? That happens over on the left side of this diagram with the memory address itself. The address acts as this highly specific routing code.
Let's break down exactly how that routing code works. If the total address length is m plus k bits, the system neatly splits that address into two distinct jobs. The lower k bits, the least significant bits, act as your bank selector. They literally dictate which physical bank the data lives in. Going back to our grocery store, these bits choose the checkout lane. Then, the upper m bits, the most significant bits, they select the exact word within that specific memory bank. So they're picking the exact item inside that checkout lane. It is a brilliant, automatic sorting mechanism, and it's built right into the physical structure of the data's address.
So, putting it all together, here's the play-by-play for a two-way interleaved system. Step 1. The controller initiates a burst access for, let's say, 4 words. Step 2. Because of how the addressing is organized with alternating locations, those 4 words are instantly spread across 2 physical DRAM banks. Step 3. Those individual memory accesses are seamlessly overlapped in time. And step 4. This overlapping completely hides the inherent physical delays of accessing the DRAM hardware. By staggering the requests across different physical hardware, the data bus just stays constantly saturated with useful data.
Of course, engineering is all about pushing things to the limit, so let's quickly talk about maximizing memory efficiency.
An interleaved memory system hits its absolute peak effectiveness when the number of memory banks is equal to, or an integer multiple of, the number of words in a cache line. And honestly, this makes perfect logical sense. If your system transfers data in blocks of 4 words, having exactly 4 interleaved memory banks means every single word in that block can be accessed at the exact same time. Getting that perfect alignment between the physical hardware layout and the data block size, that is what gives you the ultimate express lane. Which brings us to a really fascinating question to leave you with today. We've seen how interleaving brilliantly solves the bottleneck by adding more parallel lanes and overlapping those annoying hardware delays. But hardware space is finite, right? As we continue to push this time division architecture to its absolute physical limits, what happens when we simply cannot fit any more memory banks onto the motherboard? What is the next physical frontier for computer memory speed once these express lanes are completely full? It's a huge problem that engineers are battling with right now. Anyway, thank you so much for joining me today for this explainer. I really hope this deep dive illuminated some of the hidden mechanics inside your machines. Keep learning, and I'll catch you next time.